Hello and welcome. In this video, we're going to be taking a look at the AP Physics 1 review for momentum free response. Please remember to pause and rewind the video as necessary. Let's begin. In problem number 1, we're told that we have 5 objects of various masses m, all starting at rest on a frictionless surface. At time t equals 0, a constant forward force F is applied to each object for time t. At the end of time t, the force is removed. Let d be the distance that each object travels during the time t in which the force is applied. The table shows the values of m, the mass, F, the force, t, the time the force was applied, and d, the distance that the object traveled during which the force was applied. Part A. Which object has the same acceleration as object A while the force is applied? Explain your reasoning. Well, if we recall that net force equals ma, that means acceleration would be the net force divided by the mass. So let's just make a new column over here for acceleration. And that would be 4 divided by 2, or 2 meters per second squared. 2 divided by 4, which would be a half, 0.5 meters per second squared. 3 divided by 4, that would be 0.75 meters per second squared. 9 divided by 8 kilograms would be about 1.13 meters per second squared. And 6 divided by 3 would be 2 meters per second squared. So, which object has the same acceleration as A? Well, that would be E. Objects A and E have the same acceleration. So the net force in object A is 4 newtons divided by 2 kilograms, or 2 meters per second squared. And again for object E, 6 newtons divided by 3 kilograms, also 2 meters per second squared. Part B. Which object has the same momentum as object A after the force is applied? Well, what do we call a momentum applied during which the force is applied? Well, this, ladies and gentlemen, is a change in momentum or an impulse. So we're looking to see which one has the same impulse, which is force times time, as object A. Well, the force times the time of object A is 12 newton seconds, or 12 kilogram meters per second of change in momentum. So which one has the same force times time? Well, it would be object B, 2 newtons times 6 seconds. So object A and B have the same momentum because they have the same change in momentum. or impulse. Again, why do they have the same change of momentum? Because at time t equals 0, they both start with no momentum. They both start from rest. All objects are from rest. So essentially, after a certain amount of time, they have the same momentum. They have the same change in momentum. They have the same impulse. Their forces are applied over different time, but they have the same change in that momentum. Which object has the same kinetic energy as A after the force is applied? Well, again, the original kinetic energy is 0. So essentially, which ones have the same change in kinetic energy? Well, the change in kinetic energy is related to the work that was done to push the objects, which is, of course, related to the force times distance. So let's look at the chart again. This time we're going to focus on object A, force, and distance. Now we can see the force times the distance would be 36. So object A is 4 newtons times 9 meters, or we have an increase in kinetic energy of 36 joules. Well, which object has the same increase in kinetic energy of 36 joules? Well, object B, 2 times 9, that would be 18. 3 times 24, that's way over 36. Here we go, object D, 9 times 4 is 36 joules. So object D, the change in kinetic energy is equal to the work, which is equal to force times distance. And we're looking at 9 newtons times 4 meters, also 36 joules. Which object has the same speed as object A? Well, there's a couple ways we could approach this one. Same speed would be the same distance divided by time. That would be 1. Another way we could look at it, and the distance divided by time, so distance, it would be 9 divided by 3, which would be 3 meters per second. What else has that same? Well, it would be object C. Object C, 24 divided by 8. But there's another way to figure this out too. So A and C have the same distance over time. Therefore, they have the same speed. But I do want to reference another way you could figure out this problem. Remember, they have the same change in momentum. Okay, and change in momentum is equal to mass times the change in velocity. That's what I kind of want to know, is which ones have the same speed after that certain amount of time, so it's have the same change in velocity, which is force times time. So force times time times the change in velocity, or velocity, is equal to force times time divided by the mass. So essentially we could look at force times time divided by the mass, and we see that A and C, if we go 3 times 4, we get 12, divided by 2, we get 6. Same thing with letter C, object C. 8 times 3 is 24, divided by 4, again, we get 6 meters per second. So we have a couple ways we can figure out which object has the same speed as object A. In problem number 2, it says a heavy bus and a light car both start at rest at a starting line of a long track. At time t equals 0, the race begins. Both vehicles have the same constant net force during the race. After 10 seconds, the cars pass the finish line. A. Which vehicle crosses the finish line with more kinetic energy? Explain your reasoning. Well, they both start from rest. So essentially, we're looking at the change in kinetic energy. So let's examine. The change in kinetic energy, according to work energy theorem, is equal to the work that's done, which is, again, equal to the net force times the distance. Now, since the bus and the car both have the same net force applied, over the same distance, they both have the same change in kinetic energy. Part B. Which vehicle crosses the finish line with more momentum? Explain your reasoning. Again, they both have zero momentum to start with, so we're examining, they're comparing the change in momenta of these two objects. So change in momentum is equal to mass times delta V, but it's also equal to force times time. Now they have the same net force, so both vehicles have the same net force. However, the bus takes more time. And so if they have the same net force, if the bus takes more time, it has a greater change in momentum. So the bus takes more time, and therefore has a greater change in momentum. Part C. At time t equals 5 seconds, while the race is still happening, which vehicle has more kinetic energy? Explain. Well, the car will have more kinetic energy. Why is this? Well, again, the change in kinetic energy is related to the work, which is equal to the net force times distance. Now, they both have the same net force applied, both have the same net force applied. However, since the car goes faster, it will have gone a greater distance in 5 seconds. So since same net force, the car goes a greater distance in that 5 seconds, which means more work is done by the car in 5 seconds, which means it'll experience a greater kinetic energy after 5 seconds. Now, what about let's see, at time t equals 5, while the race is happening, which vehicle has more momentum? So again, we're looking at the change in momentum or the impulse. So in this case, both have the same net force, both have the same t equals 5 seconds. Therefore, both have the same impulse or change in momentum. In problem 3, we have the following scenario. In all 4 cases below, a 0.25 kilogram bullet strikes a 6 kilogram block on frictionless wheels. Rank the cases based on the block's final velocity after collision. Now, what we're dealing with here is we may use the conservation of momentum to find the final speed in each case. So in order to use the conservation of momentum, what we should do is we should find the initial momentum. That means the momentum before collision. That'll be the same case in each time, because we have the only thing that has momentum before the collision is this bullet. Notice the cart is at rest in each case. So the initial momentum is going to be 0.25 kilograms times 300 meters per second. And if we multiply 0.25 times 300 meters per second, we get 75 kilogram meters per second. This, according to the law of conservation of momentum, also needs to be the final momentum. So the initial and final momentum have to be 75 kilograms meters per second. And we will use this information to find the final speed in each case. Let's take a look. In case A, the bullet becomes embedded in the block. So that means the masses stick together. So P final is equal to, in this case, it's equal to mv, where m is the sum of the masses. So V final is equal to P final over big M, which is 75 over, in this case, 6.25 as I add those two together. V final, in this case, 675 divided by 6.25 equals 12 meters per second. Okay, it's good to work them out in each case. That way you have an idea of how to rank them. Now, in the next case, we have a situation where again, the final momentum is still got to be 75. It's got to be equal to the initial momentum. Now, here's how we find that. In this case here, the bullet passes through the block. So what's going to happen in this case is the final momentum, 75, is going to be equal to essentially mv of the cart plus mv of the bullet. Okay, we already know the V of the bullet, so we're going to solve for V of the cart. So V final, and then V of the bullet. Okay, and let's go ahead and do that. V of the V final will be the 75 minus mass of 0.25 times the bullet, which is 150 afterwards, all over the mass of the block, which is 6. And we get roughly about 7.5 meters per second. Okay. Now, in case C, you have a situation where the bullet bounces off and rebounds backwards. So if that's true, the final momentum is going to be equal to, instead of mv minus mv, let me see. So the bullet, if we multiply, so, okay, momentum of the bullet is going to be the 0.25 times 90, and it's going to the left, so it's going to be negative 0.25 quarter of 90. That's about 22.5 kilogram meters per second. Now what that means is the P final is going to be P of the cart minus P of the bullet, because it's going backwards, which really means you end up adding them. So in other words, the original was 75, and if we add the 22.5, we're at 97.5. So P of the cart is going to be at 97.5. And we'll use that to solve for the velocity of the cart. So velocity is momentum divided by mass, and we'll go 97.5 divided by 6. Velocity final is about 16 and a quarter meters per second. And in case D, we've got a case where the bullet simply hits the cart and just falls. In other words, the final velocity is 0, which means the momentum of the bullet essentially drops to 0. That means the momentum of the cart is completely transferred, and the kinetic energy is completely transferred to the cart, which means momentum final, which we already know is 75, is equal to mv final. And so it would be 75 over 6, which is 12.5 meters per second. Okay, let's rank. The highest one would be C, which is greater than 12.5, which is D, which is greater than 12, which is A, which is greater than 7.5, which is B.
Okay, let's justify this ranking. First of all, the block and the bullet actually have the same change in momentum. Let's see why this is. The bullet starts with a speed of 300 meters per second and a mass of, keeps a mass of 0.25 kilograms, but essentially starts with a momentum of 75 kilograms meters per second. The bullet in every single instance will decrease its momentum. So the bullet will have a negative change in momentum or a negative impulse, because it essentially decreases momentum due to the slowing down in all the various examples, A, B, C, and D. The block, on the other hand, starts from rest. Since it starts from rest and will increase its speed, its mass times velocity will increase. Thus, the block's momentum, the change in momentum, increases. So the block has a positive impulse or a positive change in momentum. Well, the negative change in momentum of the bullet is exactly the same as the positive change in momentum of the block. And that is how we derived the law of conservation momentum, which states the total momentum before collision equals the total momentum after collision. It was derived using this one principle here, that objects that collide essentially have the same change in momentum. One will increase its momentum and the other will decrease its momentum by the same amount. The greatest final speed of the block is the case where the bullet has the greatest change in momentum. And this is seen in KC. So if you look at KC, KC starts with a momentum of 75 kilograms meters per second. But because the bullet reverses direction in KC, it ends with a negative momentum. So it went from 75 to negative 22.5. That's a change in 97.5 kilograms meters per second. That is the greatest change in momentum of the bullet. By contrast, case B, the bullet passes all the way through, the speed cuts in half, which means the momentum cuts in half from 75 to probably 37.5, 34.5. My math's a little off. But because the momentum change of the bullet is the smallest in case B, the block's final speed will also be the smallest. So the final speed of one object corresponds to the change in momentum of the other object, if that makes sense. Problem 4. Two students conduct an experiment to test the law of conservation of momentum. To do this, they use a white car of mass 0.8 kilograms and a black car of mass 0.4 kilograms. The black car is given an initial forward motion and collides with the white car. And we can see this happen at about 1 second. The students use video analysis to create a graph of position versus time shown above, where the black dots represent the black car's position and the white dots represent the white car's position. Respond to the following two questions by writing one or more paragraphs and state your answer to the question and your reasoning based upon the graph and the given data. You may show equations and calculations, but equations and calculations alone are not sufficient enough to explain your reasoning. Is momentum conserved? Well, in order to figure this out, we have to find momentum before and after collision. Well, the momentum, if you remember, is mass times velocity. So mass are given. Velocity is the slope of the position time graph. So before collision, we can find the slope. Let's see, 1 meter in 0.2 seconds is the same as 10 meters in 2 seconds, which would be 5 meters per second. You can see the white car is going 0 meters per second. After collision, you can see the white car is moving, let's see, that's about 1.5 meters in a half a second. That's the same as 15/5. That's the same as 3 meters per second forward, where the black car rebounds backwards. It's smaller, so when it hits, it rebounds backwards. And let's see, negative 0.5 meter, and this would be, what, a half a second from 0.5 to 2. So that would be -1 meters per second. So yeah, the first thing, let's find those velocities, right? And the calculation's pretty straightforward. The initial momentum is just due to the momentum of the black car. PB is the momentum of the black car, mass times velocity. And so we simply go 0.4 times 5, or 2 kilogram meters per second. The momentum afterwards is the black car and the white car's momentum. 0.4 times 1 kilogram plus 0.4 times 3 kilograms, which comes down to 0.4 kilogram meters per second plus 2.4, which also adds up to 2. So yes, the momentum is conserved. The velocity is the slope of the position time graph, which is how we found it. The black car's velocity before the collision was found to be 5 meters per second, while the white car's velocity was 0. Thus, the initial momentum is 2 kilograms meters per second. The final momentum is the sum of the momenta involving the black and white car, which would be negative 0.4 kilogram meters per second and 2 kilogram meters per second, respectively. Is the collision elastic or inelastic? To be elastic, kinetic energy has to be conserved during the collision, meaning the same kinetic energy before and after collision. To be inelastic, kinetic energy is lost, meaning there's less kinetic energy after than before. This could be due to various things. Some of the energy could be transformed into the thermal energy of the surrounding air molecules. It could be transformed into the sound energy propagated by these air molecules. It could be essentially transformed into the work done to deform something if something, let's say, breaks after the collision or deforms in some way after the collision. There's various reasons why kinetic energy could be lost, but suffice to say a loss in kinetic energy results in an inelastic collision. No change in kinetic energy defines an elastic collision. So let's find kinetic energy. So the kinetic energy initially would be the kinetic energy of the black car, because that's the only thing moving, and it's 1/2 times 0.4 times 5 squared. Well, 5 squared is 25 times 0.4 is 10. Take half of that and we have about 5 joules. Afterwards, the final would be the kinetic energy of the black car plus the kinetic energy of the white car. And that would be 1/2 times 0.4 times the black car's velocity, which is -1, plus 1/2 times 0.8 times the white car's forward velocity of 3 meters per second. And that gives us -0.4 plus, -1 squared is -1 times 0.4, but take half of that, it's 0.2 joules, plus 3 squared is 9 times 0.8 is 7.2, take half of that, that's 3.6 joules, for a total of 3.8 joules. Still less than the initial kinetic energy. So since kinetic energy is lost, the collision is inelastic. Problem 5. The student drops a 6.8 kilogram bowling ball onto a trampoline and allows the bowling ball to bounce 1 time. The graph shows the vertical velocity of the bowling ball as a function of time, where the upward velocity is considered positive. Now, how can we use this graph to determine the acceleration? Well, acceleration is the slope of a velocity time graph. So we start there. We'll find the slope from 0 to 0.4 seconds, that downward slope right there, or from 0.5 to 0.9 seconds. Either way, you'll get a slope approximately -10 meters per second squared, right? The approximation of the acceleration due to gravity. Part B, what is the ball's change in momentum as a result? Well, the change in momentum is the mass times the change in velocity. So the mass is 6.8 kilograms. And the velocities, the change in velocities, we can find from the graph. The initial velocity would be -4. The final velocity would be 2. So the change in velocity would be 2 minus a -4, or 6. So 6 times 6.8 is about 40.8 kilograms meters per second. Now the other way we could find it, of course, is to find the momentum before and after, and 13.6 after minus a -27.2 before also adds up to 40.8 kilograms meters per second. And what is the average force applied? Well, again, change in momentum is also equal to force times time. So force would be a change in momentum over the time interval. So 40.8 Newton seconds. And if we look at the graph, you can see the collision is taking place over 0.1 second. Which gives us about 408 newtons. You could round it down to 400 or even up to 410. That would be fine as well. Again, please feel free to pause or rewind the video.